operations are encountered widely throughout productive industry in processes involving physical and chemical change. Although much of our knowledge on mixing has developed from chemical industry, many other sectors carry out mixing operations on a large scale. Thus, mixing is a central feature of many processes in the food, pharmaceutical, paper, plastics, ceramics, and rubber industries. In relation to this, we are going to introduce the mixing process as an example to be modeled using first order system. Consider only two material species, which is a solid material that is dissolved in a fluid. We refer to the solid as a solute and to the liquid as a solvent. Consider a reservoir or container that has inflow and outflow as sketched in the diagram at the right. Let Ci and Ce be the concentrations of the solute, which is in kilogram of solute per liter of the solvent. Here we denote I for inlet and E for exit. Next, we let Qi and Qe be the inlet and exit volumetric flow rates of the solvent. Thus, equation 1 gives the rate of the solute. Now, we are going to evaluate the mass balance in the solute. In general, a mass balance in any system of interest consisting of an arbitrary control volume, or Cv, can be written as rate of change of mass in Cv is equal to the mass flow rate into Cv minus the mass flow rate out of Cv. This simple expression assumes no generation or destruction, which is, for example, by chemical means. Thus, the only way to get material into or out of the Cv is by crossing the surface of the Cv solvent. Then, combining the notations from equation 1 with the generic mass balance in equation 2 gives dMs over dt is equal to Qi Ci minus Qe Ce, which is the equation number 3. And where Ms is the mass of solute in the system and the solvent volume is the Cv of interest. This simply says that the rate of change of solute in the system is equal to the net rate of solute crossing the system boundaries, which is the inlet minus outlet. And equation 3 leaves three variables, Ms, Ce, and Qe, that needs to be determined. Since there is only one constant equation, it is impossible to solve for the unknowns. These unknowns can be partially resolved by performing another mass balance in the second material species, which is the solvent material. Denoting the average solvent density as rho, the solvent mass within the system is simply rho V, and the inlet and exit mass flow rates are given by Mi is equal to rho Qi and Me is equal to rho Qe, which is equation number 4. And putting these relationships into equation number 2 will give change in mass flow rate over change in time equals mass flow rate in the inlet times the mass flow rate in the exit, or the change in rho v over dt is equal to rho q in the inlet minus rho q in the exit. Now we assume that there is no significant density variation within the system. So, rho is equal to rho I minus rho E. Then the mass balance equation will become the change in volume over the change in time is equal to Qi minus Qe. In many situations, the inlet and exit volumetric flow rates may not be equal. When this happens, we either have partial filling or draining of the system, and the solution of equation 6 gives V as a function of time as the volume of the system versus time. Knowledge of Qi and the relationship between Qe and V should allow solution of equation 6, thus giving the value of V as a function of time. This information can then be incorporated into equation number 3. Even with known volume and a formal relationship for Qe as a function of V or Ms, equation 3 still has two unknowns, the mass of solute and the exact concentration, which is the Ms and Ce respectively. We somehow must introduce another constraint equation to resolve this conflict. That is, we must somehow relate the exit conditions of the fluid to the average conditions within the CV. Although there are a number of ways to build this, the easiest and the most common method is the so-called well-mixed or continuously stirred approximation. This modeling technique assumes that the exit concentration Ce is equal to the average concentration C within the volume V, where C is simply Ms over V. This assumption occurs naturally in many problems with turbulent flow or with direct stirring of a mixture by mechanical means, and it is quite often a very good approximation. This simple relationship allows us to write the exit concentration in terms of the average concentration, or Ce, which is similar to C, is equal to Ms over V. With equation number 7, their general solute mass balance in equation 3, change in the mass of solute over the change in time, is equal to Qi minus Qe over V Ms, which is equation number 8. This system, along with the solvent mass balance in equation number 6, represents a coupled set of first-order equations that can be solved by traditional means. At constant flow rate, Q is equal to Qi minus Qe simplifies the solute mass balance in equation 8, giving the change in the mass of solute over the change in time is equal to Q times the quantity of Ci minus Ms over V, which is equation number 9. With known Q, V, and Ci, this equation represents a single linear first order that can be easily solved for the solute mass versus time. which is the ms is a function of time. Dividing equation number 9 with b will keep the equation number 10 as shown. This solution here gives C of t, the average solute concentration versus time, where tau is the fluid residence time, which is also known as the time constant, is equal to solvent volume over the solvent volume per unit time. To find the transfer function, we are going to derive equation number 10, which will become S C of S is equal to 1 over tau Ci of S minus C of S. And here, combining like terms will give C of S times the quantity of S plus 1 over tau is equal to 1 over tau times Ci of S. Finding for Cs over Ci of S is equal to 1 over tau over 1 over tau plus S. And simplifying this term will give C of S over Ci of S is equal to 1 over tau is equal to 1 plus tau S over tau. Here, dividing both sides by tau over tau will give the transfer function. Thus, the transfer function is C of S over Ci of S is equal to 1 over tau S plus 1, which after a long derivation of this function shows a first order system. That's all about the mixture problem as a model of the physical first order system. Thank you for